Hello, science students. Today I'm going to be modeling for you wind-driven waves and what are they called? Tsunami waves. And you'll find that there are quite a few distinct differences. So, as you may recall from the article in Chapter 2 of your dossier, the differences between tsunami waves and ocean waves are listed here. You can see that tsunami waves are much faster than ocean waves, and that the wavelength is much greater, and the wave height is much greater, 30 meters compared to 3 meters, You can see that in this diagram, the tsunami wave is a bigger wave, and it might not look like it in the diagram, but it's taller on average too, whereas the wind-driven waves are shorter wavelengths and they roll up on shore. Tsunami waves are so big that in this diagram you can't see that there's more waves out in the ocean coming, because they can last much longer since their wavelengths are much longer. Okay, so here's my model. This is made from simple materials. Models don't have to be super complex. This is a physical model just made from a paint tray. There's a transparency or a piece of sheet plastic, and you can see there's some water in the bottom of the tray and some nice beachfront property. So I have here a straw that I'm going to use to try to reproduce a wind-driven wave. You might have noticed that as I blew air through the straw, the houses that were closer to the shore did experience some flood damage, so their basement sheetrock is, it's going to get nasty and moldy unless they do something about that. But they probably don't have a basement because they don't live in Kansas like me. In fact, the bottom, maybe 2-3 feet of their foundation was flooded, and honestly, if it doesn't happen again, it might dry out and be okay. So those waves were caused by wind. They were much smaller, much slower, much less damage. Again, this is the wind-driven wave. Now for the tsunami-driven wave, imagine that this plastic sheeting is actually the sea floor, and it's part of a tectonic plate, right? So it's just sitting there for maybe a dozen years without doing anything, but because the plates are always moving, there's a lot of rock stress, so a lot of pressure built up. And as the pressure builds up, eventually that pressure gets released. So it's sitting on the sea floor, it's getting pushed on, it gets released. Let's see that again. So it's sitting on the sea floor. One plate pushes on the other plate, and as that happens, one of the plates gets pushed up. Now I'm going to reset some of my homes so some construction workers come in 20 years later. There hasn't been any tsunamis, and these people want to be right on the beach, just above high tide, because they want to have just a few steps to get out to the water, enjoy some paddle boarding, try not to get stung by a jellyfish. Some of the damage has been repaired. You've got some houses all along the beach here. You've got one guy that's smart because he built his house further away from shore. And as that plate gets pushed on, again, it shifts up suddenly because there's an earthquake. Before. after. So you could see in the tsunami wave that was triggered by a convergent plate boundary under the sea floor off the coast of the land that you had a wave that was triggered by an earthquake. It was much larger, it was much faster, it caused a lot more damage. So there's a great deal of differences, as I mentioned there would be. And hopefully there's not a lot of surprise there, but in a model, you are able to prove with evidence what your ideas are supposed to show.